what would the major product be for this reaction right here? Right away, we see that we have an alkane chain with a chlorine attached to it, and we have a benzene ring. So that looks like we're going to be undergoing an electrophilic aromatic substitution reaction, where we're going to be adding on our alkane here somewhere to our benzene ring. Where are we going to be adding this thing on to our benzene ring? We have to take a look at what we already have attached to our benzene ring. We have this oxygen and methyl. That's going to be a strong electron donating group, meaning it's going to favor the ortho and para positions. What do we have attached to this carbon? Well, we have a carbon here, and this carbon has two hydrogens. It's also going to be an electron donating group, but it's not going to be as strong. It will favor the ortho and para, and this one will also favor the ortho and para. Now, which one's going to have priority when deciding where we're going to be adding our molecule on? This group right here, or these two groups right here? Well, oxygen and methyl is a strong electron donating group, meaning it's going to make our benzene ring more reactive. It's giving more electrons than these two substituents there. Because it's a strong activating group, it's going to have priority over these two. So we're either going to be adding on our substituents in the ortho positions here or the para positions. We just have to figure out which one we're going to be adding it on now to. Can we add it on to our para position? No, we can't, because it's getting blocked by this thing right here. How are we going to add it on when something's blocking it? What about in this position? It's an alright spot to add it on, but there's a lot of steric hindrance here because we're putting two large molecules next to each other. Our only other option is to put on our alkane chain here. How are we going to be attaching on our alkane chain? Let's go ahead and do the reaction mechanism to figure out how we're going to be adding it on. The first step in our reaction mechanism is going to be activating our electrophile. How do you do that? Well, we have our Lewis acid, and chlorine is going to go and attack aluminum. We're going to form the following intermediate where chlorine is bonded to aluminum and it's positive, aluminum's negative. We have something here, okay? Let's take a look here. This is a primary carbon. What do we have next to it? We have a tertiary carbon. Are we going to form a carbocation on a primary carbon or a tertiary carbon? Obviously, we want to form the carbocation on our tertiary carbon, and that's exactly what we're going to do. We're going to undergo a 1,2 hydride shift where the hydrogen is going to jump down and form a bond there, which is going to cause this bond to break. Super sneaky. Now that we have activated our electrophile, our benzene ring has no other choice but to go and attack that positive charge. And that's exactly what it's going to do. It's going to use its nucleophilic pi bond to go and stabilize that carbocation. And we're going to form the following intermediate. We've attached our alkane chain on, but this guy right here lost an electron, meaning he's positively charged. Carbocation, super unstable. We have obliterated our benzene ring. We need to figure out how to regenerate it because benzene rings are super stable. How are we going to regenerate it? Well, we have a hydrogen here. And remember, we have our AlCl4, and chlorine is just gonna go all the way over here and steal the proton. Chlorine's super selfish. Hydrogen can have how many bonds? One bond. So we have to break this bond here, and these electrons just jump back into our ring to help and reform our benzene ring. And we'll be left with our major product